In this video, we will discuss a very, very important property of continuous functions. So this is one of the foundation results of calculus. So let's see what's that, right? So let's see, we start from a very good function, as we just mentioned, a continuous function. So we suppose our function is good. Suppose f here is a good function, which is continuous, right? Recall that being continuous means the limit at any point in the interval or domain is equal to the function value at that point, which means you don't have any gap or hole or vertical asymptote, right? So on a closed and bounded interval from A to B, right? A, B are finite numbers from 1 to 2. A might be 1, B might be 2, A might be 0, B might be 10, right? So, and we have one more assumption, and we choose a number between f of A and f of B, right? Let n here, capital N here, be a number, arbitrary number, but with a small restriction between f of A and f of B, right? I try to sketch a picture, see what's going on here. So you are given a function, right? We are in a xy coordinate system, right? X, y here. And we are given a closed and unbounded interval from A to B. Then we have a good function, which is continuous, right? Something like this. We have two function values at endpoint, which is f of A here. F of B is somewhere here. Then we choose an arbitrary point in between them, right? Between f of A and f of B, let's call that n here. So let's see what happens. Then you draw a horizontal line whose value, y value equal to n here. Sketch such a line here. And because the function is continuous, you don't have any gap or hole or any vertical asymptote. So which means there must be a C such that f of C, a C is between A and B, the intersection point, right? There must be a C which is between A and B such that f of C, the function value at C, equal to the given number n here, right? Then so this is our conclusion. So it's quite easy to see that from our picture, but the proof is very hard, and so we'll skip our proof and just see the application of the intermediate value theorem, right? So then what happens is there is a C which is inside the interval AB, because C is a number between f of A, f and B, so for sure it's different from f of B, right? Such that f of C here equal to n. So this is basically what's going on with our intermediate value theorem. As I said, this is one of the foundation results in calculus, right? Basically, so that's why we deal with continuous function in most of times, right? Let's see an example, like how do we apply? Let's say a very classic application of intermediate value theorem, right? So in math, one of the things we do is solve equations, right? So we have an equation here, which is 4x cubed minus 6x squared plus 3x minus 2 equal to 0, right? We want to solve it for sure. You can see that this function is very hard to solve, right? Now, what we want to do here is we want to show that there must be a solution between some two numbers, but we don't know what's the solution, right? We want to show that there is a root of this equation here between between 1 and 2, right? Between 1 and 2. Let's try to do that, right? So let's see the solution. So what we want to do here is we want to get a root, let's call that C, right? Such that if you plug in C, you get 0. Plug C on left side, you get 0. So left side is our function, right? So let's give a name for our function. So let f of x to be our function, which is 4x cubed minus 6x squared plus 3x minus 2, right? So you want to show that there must be a root in between, right? How do you show that? All you need to do is you calculate f of 1 and f of 2. If 1 is positive, the other one is negative, then 0 is in between them. Then we can apply the intermediate value theorem to guarantee there must be a root in between 1 and 2. So that's basically our idea, right? But before we apply our intermediate value theorem, we need to see that is our function continuous, right? This function clearly is continuous because that's a polynomial by our discussion. Polynomial function, the domain of polynomial function is all real numbers, and this function is always continuous, right? By our discussion before, right? So we know that. Then this function f here is always continuous everywhere. So for sure it's continuous on the interval we are interested, right? On R. So hence on the interval from 1 to 2, because this is the interval we are interested for sure. We know that. Now we want to calculate f1 and f2, right? f1 plug in 1, right? You get 4 minus 6 plus 3 minus 2. So this is negative 1, right? f2 will be 32, 4 times 8, 32 minus 24 plus 6 minus 2. So this is basically 12, right? One is less than 0. The other one is greater than 0, right? So clearly that means 0 here is between 0 is between f of 1 and f of 2. So that's the number we are choosing, right? Capital N here. So then by the intermediate value theorem, right? There is a C inside 1, 2, such that f of C here, which is 4c cubed minus 6c squared plus 3c minus 2 equal to 0. So this C is the root of our equation. So this is a very classic application of intermediate value theorem. So intermediate value theorem is one, as I mentioned a couple of times, this is one of the foundational results in calculus.